bunch of very interesting questions, because of course there is a lot to say, and sometimes I'm asking some details, and I will refer also to the questions I got for. So first of all, yeah, sorry again about the fact that I didn't put this alpha term, that is the one of the local oscillator amplitudes in the quadrature that I'm measuring actually via homodyne detection. That is very important to get the amplification of the signal. And I'm also writing it in terms of Q cosinus of theta, P sinus of theta, that maybe is easier to look at. And I mean, of course, this theta is the one that is chosen on the local oscillator side, is the difference of phases between the two, that you can set with a piezo on a mirror. Or, I mean, if you're in a telecom regime, you can use an electro-optic, a phase modulator under the electro-optic. And you can, if you set to 0, you measure Q. If you set to pi over 2, you measure P, and everything in between, actually, you are measuring something that is superposition of the two. So then I go back to my two-mode squeeze state vacuum, and some of you was smart enough to see that here you have equal to EPR state. And I want to speak a little bit what does it mean, and I mean the difference in jargon in DV and especially QKD stuff and CV. So EPR stays for Einstein-Podolsky-Rosen, and very often actually in DV, QKD, you use EPR for speaking about the maximally entangled state, okay? Historically, actually the EPR state was more close to this kind of state, because actually what really Einstein-Podolsky-Rosen did was to take a system where you have position and momentum of two particles that are, I mean, then you, with all that are entangled. They were not speaking about entanglement, it was more about the fact that the quantum mechanics was complete or not at the time, but, and of course there are fully entangled, meaning that you really get this delta correlation between the two. And here, the kind of delta correlation, you get it if your squeezing is infinite. So in continuous variable, when you speak about these EPR states, the maximal entangled state, either you say does not exist, they does not exist in real life, because it's the one where the squeezing is infinite. Okay, so this concept is not used a lot, okay? Still, actually, the amount of squeezing is important. When you stay with Gaussian state of light, this is very well defined, even multi-mode category of state, squeezing and entanglement are the same results. Because the entanglement I get comes from squeezing, so you can always, we're going to comment more when we build the network, the entangled network, is the fact that actually all the entanglement you get come from the fact that at the beginning you have some squeezing and you make squeezing state interfere, okay? This is not true anymore with non-Gaussian states. And it's very hard to treat non-Gaussian states, multi-mode. I have a bunch of friends and colleagues that work on it, and it's a full career problem. Okay, very good. And you're going to see that actually the fact that we don't have the maximally entangled states makes that the teleportation that we do in CV by encoding in CV is a little bit different by using the CV resource. And also state differences between the two fields that is going to hold also in quantum computing that you can do with this kind of state. Okay, how is the protocol? So I start with the ideal case. Ideal case is the fact that I really have a state that can describe as delta function correlation, okay? So I have these CPR states, I have two modes. You can really think about, the first experiment that has been done is the fact that you really have a B-splitter. It can be described as a B-splitter, at least two modes coming from a OPO, and one is sent to Alice, one is sent to Bob. And then actually you do, so in the discrete prior case, you do bell measurements on the Alice side, and you mix the state that is coming with the portion of the PR state of Alice, and you do bell measurement. In this case, we do homodyne measurement. I'm going to describe everything by following what is going on to the operator, X and P. of course, then at the end, I mean, you know, when you do this Eisenberg picture, what you can get is that you can get expectation value from what you get. The full treatments use, you have to use Wigner function, the same way actually in the discrete variable case, you have to follow what is going on in the discrete variable. I mean, the result is going to be the same as this is a C. Okay, so what you do is that actually you mix on any side on this 50-50 B splitter, and on the two sides, you measure on one side either X or P, and actually you get the two local oscillator arriving on the two sides. You have a phase shift between the two. So if one is measuring X, the other one is measuring P. These plus minus refer to one of the two outputs, actually. So these are the observable that you could measure. Of course, if you measure X plus, you're measuring P minus. So the plus and the minus actually are the two parts. What I consider the case where I measure and I get a specific value that is X tilde on the minus part and P plus tilde on the other side. So this, of course, is correlated to the quadrature value that I had at the entrance of my B-splitter, both the state that I want to teleport and the EPR, one of the two portions, the EPR beam. And as this holds, the fact that you have exact correlation between the two, well, of course, actually, I can redescribe the XA and the PA with respect to this value that I measure and the initial part. Well, it tells you that the value on both sides of X is exactly the value of Alice side, while the value on both sides of P is minus the value of Alice. So if I can relate what I've measured on Alice side with this value of Alice, I can do it for both sides. And then, of course, you see that actually this value here of Bob is exactly the value of the initial quadrature. These are the state that I want to teleport, plus a term here and here. And this term, actually, Bob want to get rid of this term. So what it does is that it waits for Alice telling him which value she measured, because this is exactly the value that Alice measured on the homodyne. And then he builds a coherent state that is based on the value that Alice measured. It's sent on a high reflectivity beam splitter, such that actually this is a displacement operator. And so actually displace the value to the initial one, actually get rid of these two values that Alice gave, okay? So what is the difference and what you can tell? I mean, I'm doing it in a very simple scheme. Again, I'm just looking at what is going on for quadrature value. You can describe this one, the full process, by using Wigner function. And at the end of the day, I mean, by knowing this value and doing the displacement, you see that the Wigner function at the end should be displaced by these two values in order to get, is really the Wigner function of the initial state, okay? So, okay, you don't have Bell measurement here, you do homodyne measurements. And the fact that you measure specific value, it gives you a relation that is specific one with the entering terms, and directly projects actually the EPR part on both sides on specific value. And then you have to correct by displacing from these terms here. So you see that one of the difference, this is the first difference compared to the discrete variable, is that homodyne we can run at any time. The Bell state measurements, so now you have very much efficient photon counter. So probably you can get a very high rate of measurements, but you don't always measure the same Bell state, and actually you are not measuring continuously the Bell state. Homodynamic is always there. So it's a deterministic measure that is always there. And actually, instead of getting the information on which Bell states Bob has measured, really get the measurement of the correction that Bob has to do, that in this case is a displacement, in the discrete bar you have a rotation of the qubit depending on which state you get. Okay, so this is the first difference. Yeah.
That one is also a beam splitter on right side?
Yeah, so this one is a beam splitter, where actually you mix your states. So this is a high transmittivity beam splitter, and you get a part. Actually, there's a coherent state coming here that is reflected.
It's the classical signal.
It's a classical signal that Bob builds, knowing the measurement that Alice has done. Again, I have to tell, so this is kind of a pictorial way of doing it. What you do is not really that you can think about having a laser in which you tune X and P. Actually, what you do using electro-optic modulator to give some specific amplitude, the phase of a specific electronic frequency, and then actually you mix it with your system. Okay, so then the other difference is that I told you that we don't have the maximal entangled state. And so actually, this is the Wigner function of the EPR state that I can build. That is very much dependent on the amount of squeezing I get, okay? And the correlation that you have between X and on the Alice side and the Bob side can be written as the correlation they could get from two values that are drawn from vacuum statistic, and then you multiply by a squeezing factor. Okay. Of course, if the squeezing factor is infinite, you get the delta correlation that I was using before. If it's not the case, actually, you get some noise in what you're doing. You get some vacuum noise entering. Okay. Okay, so this is squeezing, this is the vacuum. So how is going the treatment I've done before in this case? So actually, you change actually the relation that you have between Bob and Alice. So X of Bob is equal to X of Alice plus this noisy term, okay? And the same for Bob. So actually on Alice's side, nothing changed. You do the same measurement, but then actually when you look, so this is what Alice measure actually. So sorry. So this is what is the quadrature of Alice on this has measured X minus, okay? And you thought that is equal to the one of Bob. So this term is this as before, but then you have to add this noisy term, okay? And the same on the P quadrature. So at the end, of course, Bob again wait for the communication of Alice telling him what were the values she measured, and he does the displacement, but you cannot get rid of this term, okay? So at the end of the day, what you get, if you look at the Wigner function treatment, is that you get the right state at the end, but it's mixed with the Wigner function of a vacuum. And how much is this component? It depends on how far you have squeezed or how less you have squeezed actually the state at the beginning. So this is the second difference of continuous variable quantum teleportation, is the fact that you can never get a perfect result, meaning that the fidelity can be close to 1, but can never be 1. You always have a portion of the vacuum state that is mixed, because you always have a term that is, you have a noise term here, that is known if the squeezing is large, but cannot be 0. At least not in real life, because infinite squeezing means infinite energy, okay? And actually, these two differences very much hold in whatever kind of quantum computing, quantum information protocol you can do in discrete and continuous variable, at least in optics, is the fact that very often in the discrete variable case is never fully deterministic. Okay, you have photon counters approaching efficiency 1, but the kind of protocol, I mean, you have to wait for them, at least for the photon being there. Also, I mean, you have very nice photon source now approaching. They're kind of semi-deterministic, but the probability is never 1, neither of producing photons and or detecting them. So still keeps a deterministic part on, you have to wait for the detector to click in order to say that you have this best state measurement. While continuous variable is not the case, we use resource that can be deterministically generated. So the squeeze state is always there if you do, and we're going to see it in 10 minutes, if you use the right protocol. And the homodynamic measurement is continuously measuring the homodynamic measurement, okay? But on the other side, I mean, in a way, what you do in discrete variable, you post-select for the click, but what you get, the fidelity in principle can be 1, if you do things in a good way. On the continuous variable, you always get some noise. So you see, so this is the drawback, actually. In a way, it comes from the fact that the homodynamic detection is measuring vacuum. Well, when you have photon counter, you are discarding the vacuum part, because you post-select only on photon counting. So it's the reason why actually you get back the vacuum in the processing in continuous variable, because homodynamic detection measure everything. Okay. Well, we can discuss about the fact with perfect photon counter, if they're really perfect, when they don't detect anything, you can tell they detect 0. But this approximation needs to have efficiency that are very, 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 very high, and you normally don't use too much in protocols, this point of view. Okay, do you have question on teleportation in continuous variable? Okay. I mean, if you have question later, we can also ask. So I'm switching presentation, because now we're going to come back on the network and the kind of entanglement network that has been defined in a quantum computing protocol, measurement-based, that I also am going to use for other cases. And I also want to speak about, so at first I'm going to coming back to these class states, a little bit on the more theoretical side, and then telling you how we build them experimentally, okay? Very good. So class state in quantum information protocol. So I go back to these concepts I was introducing before, where you have this class state and so on. And I mean, the teleportation is very important because this process is nothing else than a generalized teleportation, okay, whenever you're doing discrete and continuous variable. So if you learn the difference of teleportation in discrete and continuous variable case, you more or less have the differences that are going to appear here also in this kind of measurement-based protocol. Yeah, this is what I'm telling, is a generalized teleportation. Okay, now I'm going to show you some very mathematical slides that I'm going to comment. So in the slide you find the full calculation. I'm going to giving you the concept. Of course, if you have very specific questions, I'm going to answer the question. But I don't want to spend a lot of time. So one concept that is the underlying paradigm of the measurement-based scenario of quantum computing is what is called the teleportation gate. And here I'm giving you the circuitry representation of the teleportation gate in continuous variable. So what you have here is that you start, hysteria with what is called an infinity squeeze state, because this is actually a state with a well-defined quadrature, P equal to 0. Is an unphysical state, it's not normalized, but you can use it for doing calculation, okay? On the other side, I have a state that is entering, and here actually what I'm doing, I'm applied the CZ operator I was telling you is the entangling gate that we use in continuous variable. On this side, I'm measuring quadrature P, so here is just a representation of an homodyne detection measuring P, and I'm getting a value M. And I have a state at the output, okay? So these states at the entering, I can represent this way. So actually, remember, this was the way I was giving you the superposition principle in continuous variable, is that I can write any state as a superposition of any value of a quadrature. So this is in the position representation, meaning this SP, SQ actually is nothing else, a state, right? Eigenvalue. So what I'm telling that's actually, probably is here, yeah, sorry, it's written, but by the way, I write also here is that when I apply the operator Q on these states, I get S, which is an eigenstate of this operator. And I can also define on the P case, huh? So I can define eigenstates of the operator P, same way. So this means that the 0, 1 is the one that has as eigenstates S equal to 0. Again, these are physical state because you cannot normalize them as quantum state, but they can still use as mean of calculating everything. So actually I have amplitudes of phi s that define actually how this state is described in this basis. And then I go bunch of calculation that are based on the fact that Q and P are the displacement operator of the other. So when you apply, I mean the generator of displacement, sorry, for the other. So if you apply e to the I Q operator on a state with well-defined P value, you get this value displaced by this value. I mean, I can go through the full calculation. It's fully written in the slides. It's a little bit boring, but what you do is actually you tell that, well, I measure this value M for the quadrature P1 on this after I have applied this operator on these two states, arriving on the two modes. And then I start to write what is this state. I start to see what are the displacement operator. I rewrite stuff that way. I do another bunch of calculations. This is what I was telling, that I always play with the fact that actually Q is the generator of translation in P. And you can also define that the state SQ1 is the Fourier transform of the state with a specific defined value of P. And you use it, and at the end, actually, I'm going directly to the results because this could be a full classes of how you do it. I really wanted to show a little bit the procedure. Of course, if you're interested, I mean, we can also discuss a little bit later how you do calculation. The full calculation is on the slide, so you're going to get the slide. But at the end of the day, what you get for the state at the output here, you get actually the Fourier transform of the state entering here that is displaced, so this xm, by this term, that depends on the measurement that you have got on this value. So it's a kind of teleportation. So from here to here, you teleport the state, but you also apply a Fourier transform and a displacement on X, because P is generating the translation on X, okay? Again, if you're interested about the full calculation, we can discuss also later on. Okay, so this is the first step. The second step is the fact that instead of doing this measurement, that is a quadrature measurement, you do another measurement, and you can describe this as doing this. So the operator actually that you're measuring is this dq dag p dq, where dq is the exponent of any function on q. Okay, I'm not telling you how you can do it experimentally because it really depends on the shape of this function here. But for the moment, I'm just keeping very general. So this is just a real function of q. And actually, I can see that, well, this is the observable that I'm measuring is no more. As this dq commute with the Cz, actually is like if, I'm applying this dq on the state before doing the Cz. So actually, I'm teleporting dq phi, and then I'm applying the Fourier transform and the displacement. Why this starts to be interesting? Because, the Fourier transform and the displacement is a byproduct that I get from the way I define this teleportation gate. But the FQ, if I'm smart enough as an experimentalist, I can devise, my experiment in order to do the f of q I want. So this is a way I am just trying to apply something as a unitary transformation, okay? Then the other thing that I can do, this is a bunch of very bad calculation. Again, it's fully described because if you want to go, you should be able to do on the note. I start to concatenate the quantum teleportation gate, meaning that this is the first part that I was describing before, and now actually the output, I do again a Seaside operation with another unphysical state, which is an infinity squeeze state on P. I apply another operator, so this D prime is just because I want to choose a different function of Q at this step. And then I get, at the end of the day, this result is that I get my initial state where I applied this D operator that depends on a function of Q. And because of Fourier transform and, let's say, commutation rules of Q and P, this D prime now is applying a transformation effectively on the state that depends, is a function of the P operator, displaced by M1, that is the results I got from a previous. And of course, I get as byproduct Fourier transform and displacement. Okay. So by concatenating elements, I get function of Q and P alternatively. That depends on the function that I decide, but it depends also on the measurement I have done before, meaning that if I want to apply a very specific function, I should wait to get the results of the measurement before so that I can correct the operation I want to do in order to take into account this M. Very good. Also, this is exactly what I just told, is that you can actively apply an operator that depends on the quadrature. We need to adapt to the measurement observable, and so on. Actually, this is the reason why we arrive to the cluster, is because actually, well, you can keep doing it sequentially in order to really build the kind of operation you want to do on your quantum state. And you see that you are entering again with screen state and CZ operation. And the fact is that the CZ commute with the operation that you do here. So even if sometimes arrive later on the measurement you have done, actually you can put on the beginning. Okay. And these set of state with CZ operation is a definition of a cluster state. In particular here, the way I've devised actually the calculation is that I'm building what is called a linear cluster. So this is the graphical representation you very often have of cluster. You have balls and link. So the balls are different modes of light. Okay, again, you have, I think the easiest way of representing it, you can really think that they have different paths on your chip, if you want to have a chip with a photonic chip where you get the squeeze state arriving, that in principle they should be infinitely squeezed. Of course, you cannot get them. And then you have this Seaside operation that entangle them, and then you get actually this cluster state. Okay. So more generally, if you want to do any kind of operation, you need to have a bidimensional cluster. Okay. And so this is the definition of the bidimensional cluster. You have a bunch of infinitely squeezed states, and you apply the CZ operation given a specific adjacency matrix. So this is the adjacency matrix of the graph that I'm showing, okay? That contains 0 and 1, telling if you have applied or not the CZ between two specific modes, okay? What you do is that you define a set of input modes and a set of output mode in this cluster. You encode a state in one of the inputs, and then you measure the vertex of the other, except the one in which you want to read the in the basis that is given by this one. I mean, it's really a combination of this function that could be a polynomial on Q. And then the remaining amazing mode encodes the operation you have done at the end. Do you have question up to here? So this is a very theoretical scenario, but please, if it's not clear, ask.
I think the topology definition of the CV process is similar to differences between copying and not copying with inclusion of matrix 3.
Sorry,
the role of the to define the closed system.
So maybe I can tell you what is the practical difference between the
DV and CV. Like, I mean, DV, like, we do not have the variable like free in the definition.
So, so actually, in the DV case, you start with qubit states, of course, actually that are, I think, are on the plus and minus basis, and then you apply the CZ gate between them. Okay. And this you can do if you're smart enough. You can do in the lab. In the continuous variable, the theory tells you that you have to start with infinity squeeze state, and then apply this CZ operation. Well, I told you that we cannot have infinity squeeze state. So actually, what you can realize in the lab is an approximation of the theoretical one that are defined.
So my question is, does V has any physical role there?
Physical role, meaning what you're asking me, what is the physical operation?
Like, defines the closure state there. So since the V is kind of a variable, which is not exactly related to topology.
So yeah, I mean, it's very much linked to the topology. Actually, this VIK. I mean, for example, this is the one of the grid in this case. Okay. Then I have to comment on it. The first one is that even in the discrete variable case, you cannot use any V to doing universal quantum computing. There are shape of cluster, or at least more generally we speak about graph state, meaning that you have this, because you represent them as a graph. And depending on the shape of the graph, you can do universal quantum computing or not. For example, I mean, if I use a tree graph state here, I mean, you cannot do quantum computing by, what you want to do is just local operation and measurement. Okay, so you want to show that if you just do local operation and measurement, you can do any universal calculation. I mean, any calculation, universal calculation you want, and not any shape of the graphs work. Okay, And this is true also in continuous variable. Then actually in continuous variable you cannot get it. You are going to get just some approximation. So at the end of the day, this CZ operation can be done in the lab, and again, they are squeezing n B-splitter, the way you can implement it. So everything that has to do with clustering continuous variable, you have to measure squeezing, the best squeeze that you can, and making linear optic transformation. And we're going to come more clearly later on it. But of course, actually, you can never build this theoretical one. Okay, it's just a limit of the one that you can get. The other point is that if you want, I mean, I was not telling how operation you can implement this measurement. Of course, if just P, I'm telling is a homodyne measurement. As far as our Gaussian operation here, you can still do some homodyne or heterodyne or double homodyne, depends which one you prefer to. Kind of dyne stuff, meaning that you still have a local oscillator coming and you make measurement the way I have defined the homodyne, and linear optic stuff. But in very general, if you want to have polynomials that are of the third order, you need to be non-Gaussian, probably have to include some photon counting experiment that give you some non-Gaussianity to your system. So homodyne is not enough in any case, if you want to really be universal. And this is actually, I mean, this is always device, I guess, in the slide before I was showing the reference, to paper on continuous variable cluster state computing of Nick Menikuchi and Milsgu. They came out in 2009. People are trying to implement stuff. Of course, there were no idea of fault tolerance on it, okay, yet. Still it's hard to do it. Then option you have to go to fault tolerant. Before telling how we in the lab implement with this cluster state and what is the quality, I just want to give you an overview of what is done now, in the sense of if you really want to fault tolerant in this scheme. At first, we speak a little bit less about the differentiation of continuous variable and discrete variable. We mainly speak about bosonic quantum computing, fault tolerant. So this is a more recent paper. It's not the most recent neither of, so Xanadu is, I mean, you have a lot of startup working, quantum industry working on photonic implementation of quantum computing. The one that they do is the one that is closest to continuous variable principle, meaning that they really want to use homodyne at the end of the day for measuring the calculation they do. So the way of viewing code information is really encoding continuous variable. And this is a paper about a fault tolerant, a proposal for a fault tolerant optical implementation. And you see that they have here scheme for something that looks like a graph. I mean, it's a graph, so you can think that this is your cluster state. And it's three-dimensional now because they consider a very specific dimension is time. So each time you have a bunch of modes that could be, I mean, in this proposal they have different spatial modes, different paths on a chip arriving. But also actually, you really need to bring some non-Gaussian state on these nodes. And these ideal non-Gaussian states are called GKP states, for the name of the three people that devised that theoretica for the first time. And they're kind of very exotic. So the Wigner function of this state is composed. So, I mean, the fully theoretical one is that you have an infinite amount of peak on the phase space, positive and negative. So you can see why they can be used. I'm not going to speak a lot about it, but how they can be used as in fault tolerance, because if you have error that comes from it's also called grid states, so kind of grid in phase space. So if you can really check error, and actually you can define in 0 and 1 state as being two grids that are displaced. One is in between of the other, and then actually you can really use this as a ruler to do your fault tolerance implementation. Again, I'm not going to give a lecture on this, but just to give you the full scheme, it's possible, is there. So in this case, you need a lot of these little beasts for getting fault tolerant. And why you have this time scale is just because, I mean, either or not you're able to generate non-deterministic IDs, meaning that you get them because you have done a bunch of photon counting somewhere. You go on and you keep building this structure, waiting for the next coming. And well, you can find details, but it also has some more recent results. What is the state of the art of what we can do in optics for the moment? So generate this kind of structure, being fully Gaussian, it's possible, and you can scale a lot. So these are three structures that have been generated. So one is in the group of Akira Furuzawa, also in Tokyo, not far from here. The other one is the group of Ulrich Andersen in Ligny, not far from Copenhagen. And this actually is the structure that probably, of course, you have heard about because it's the one of that Xanadu was using for doing the quantum adduction, meaning that you build this structure and then you do photon counting. But just the structure before you do photon counting is a class state. Okay. And this kind can be infinitely long if you use as degree of, I mean, your mode is a specific time beam. I'm going to come back again on it. So, I mean, the generation of the cluster states in continuous variable is easy to scale, or at least easier than in this case, still you have to work a lot. Yeah?
People ask more explanation how do you want to generate cluster states? How do you build
It's going to be the after it. I just wanted to give you the big picture, and then I'm building the cluster state. Okay, one by one. This is just the state of the art up to now. The second point is that you need to introduce this GKP state. Okay, up to last year, I was telling that the best results on GKP again was done in the group of Akira, and this is kind of the structure that you can get. Well, if you go in other infrastructure, meaning microwave interacting with superconducting device, you can build nice GKP states. Still, but they have problem to have multi-modes. So each platform has the advantage and the drawback. Xanadu got a very recent results by getting a first nice photonic GKP state. Still, actually, I mean, I don't think you can do fault tolerance with this state. It's negative enough. But I mean, experiment is a very good result for it. So this gives a little bit the state of the art. And now I can go on how we build the cluster state that I also want to use in the protocol. Okay, so the idea is that if you just take a two-node cluster state, it really looks like the two-mode squeeze state. Of course, I mean, the theoretical one has the squeezing is infinite, you can never get it, but it's exactly the same. It's the same in terms of resource. It's not the same in the sense that in the cluster state, the kind of correlation you get are among Q of each node, sorry, P of each node and the Q of the other that are linked together. So for example, if I take well, I just take, in principle, this is a linear cluster, so I can devise that like that. So this is the node 1, the node 2, and the node 3, okay? If I take what I call, another operational way of defining class is that you define operators that are called nullifier, that are very much linked to the stabilizer for the one that I use to the discrete variable case. And the nullifier of the node 1 is just P1 minus Q2, because it's linked to the node 2. The one of the second node is P2 minus Q1 minus Q3. The one of 3 is P3 minus Q1. And another way of defining the class states, theoretically, is to tell that there are eigenstate of this operator with eigenvalue 0, meaning that if I apply this operator to my cluster state, so the one that I had defined before with the adjacency matrix and so on, this should give me 0. Okay, and the same for any. Okay. The one that you get experimentally, so in principle, if this is 0, it means that actually for a cluster state, you should have P1 minus Q2 equal to 0. Every time you measure that, you should have this correlation, which is kind of delta function, okay? And so you get this delta function. You know very well that you cannot get it experimentally, but experimentally you can squeeze this difference. It's exactly what it is, the two-mode squeeze state. It's not among Q1 and Q2. You have P1 and Q2. I mean, it's just a phase factor, and it depends how you define, and you can add an extra phase. But I mean, it really looks like being the two-mode squeeze state, okay? And actually, this is the way you build your correlation. So if you have just two nodes, it's the two-mode squeeze state. So it means that if you have squeezing and linear optics, I can build my class state, okay? The full equivalence between the two, I mean, the operational way I have described before is that you have squeeze state, and then you apply a CZ operator, okay? This is, I mean, these two squeeze modes and the CZ operator is equivalent to have squeezing from the beginning and applying a linear optics, meaning a B-splitter. It depends the way you define things. The full equivalence mathematically is true when you go to infinite squeezing. Operationally, it's true in any case if you allow to have a different amount of squeezing at the beginning. What I mean is that having two squeeze states, so in principle, they should be infinitely squeezed, but get rid of it. Arriving on two paths and applying a CZ operator, okay, is equivalent to have a squeeze state arriving on a B-splitter is fully equivalent even for finite squeezing if you allow the two squeezers to have a different squeezing value. From where it comes, this? This comes from the fact that any two-mode, but even multi-mode Gaussian state of light can be always decomposed as linear optics and squeezing. And this comes from what is called the Bloch-Messier decomposition. So the way it's devised and is written normally is the fact that I'm describing again my quantum state using quadrature operator, okay? And I have a process that produces Gaussian state of light. It can always be described as quadrature, where you can have what is called a symplectic operation on them. And you can start from vacuum, for example. And you can put in the symplectic also the fact that you can have displacement. But these symplectic transformations are all the ones that you can generate with Gaussian Hamiltonian, meaning the one that up to the second order in quadrature, okay? And this can be decomposed as, forgive me, I never remember if the transposing is here or here, but I will check. It also depends how you define. As a bunch of operations that are, these are orthogonal transformation, and I mean, they're just linear optic transformation. And this delta is, the fact that you're applying is a diagonal matrix where you have squeezing terms applied to the quadrature, okay? I'm speaking about pure states up to now. This is also an important point. But any symplectic transformation, meaning operation, the one that can be built starting with Hamiltonian that are most quadratic in quadrature, can be decomposed in squeezing and displitter. Okay? The Seaside itself is an operation that has some squeezing in it, meaning that if I do the block messiah of this operation, I get some more squeezing and linear optics. Is the reason actually, if I start with two squeeze states with the same size and apply CZ, I don't directly get the same squeeze state here and the B splitter, but I should change a little bit the squeezing on this side. Okay? But this is very important. So here I'm just picturing two nodes, okay? But this is general. On any pure multimode Gaussian state can be always decomposed in squeezing and linear optics, plus some displacement. Of course, if you have a mean value of the fields, this is done by displacing. That could be done with the coherent state and the missplit. Okay, now that I have two nodes, I would like to have more than two. And I start to speak about the kind of process in which you can get at first the two nodes and then more than two, which is the parametric process. So this is a parametric down conversion process in which actually you go on a Chi2 crystal, you pump the crystal, and this is the Hamiltonian you get for the signal and hydro fields. How many of you have never seen this Hamiltonian, this operation? Very few, okay. No, that's good, at least one. So actually, you have a Chi2, so a nonlinear process, and on the quantum description, you get that one of the photon, at each time you have that, you get this process done, is that one of the photon of the pump is transformed in two photons that are called signal idler, and you have, this is the energy conservation, okay, that you get. And this is the kind of Hamiltonian that you can devise for, that you can write for this process with a lot of approximation. So I can give a full lecture on how you can treat it on linear optics and which kind of Hamiltonian you have to use. In this system, very often you treat the pump, meaning these fields, as classical. It's the reason why you don't have any operator in and out appearing for these fields. So these are the operator for the signal and the idler. And actually you have the amplitude of this pump that is appearing in this Xi factor, in which you have also the Chi2 term of the nonlinear optics. This process is used for getting squeezing when the two fields are degenerate, and very often in the book you are told that you put it in the cavity. It's not anymore the case. You can do single pass squeezing on parametric down conversion, but because you want to have an eigen, and actually you see that when you have degenerate field, it means that the signal idea is exactly the same. So you get this Hamiltonian here. This is exactly proportional to the squeezing operator I was showing before. This is one that squeeze when you apply in a vacuum state. But also you get that if they are non-degenerate, meaning the signal and the idle fields are different for some reason. They have different frequency, they have different direction, they have different polarization. Well, actually what you get for free in this case is the two-mode squeeze state. And maybe you can understand, I was telling you that the two-mode squeeze states, you get it when you have two squeeze states and the basis change, is what it is, a B-splitter. Well, actually going from this Hamiltonian to the previous one, sorry, the degenerate in a way you get a basis change. Consider you have twice the squeezing. And so you get, let's say, the first block, the two-mode squeezing for the class. I'm building the class state. Huh? I skip for the moment the interlude because I want to, otherwise and I go back to the interludes later on. Okay, very good. So how I can have many, so if you take this picture, the way you think it, is to have many squeezers, so many squeeze states, for example, on different paths. This could be a physical picture, arriving on an interferometer, it's a linear optics. And then at the end, you get at the output, the physical output, you have different modes. And these modes are the ones that are represented by a graphical structure, which is the one of the cluster, where you put the link, well, it depends which kind of linear optics you have done. You can imagine to have a B-splitter from this and this, or to have one from this and this one, and you add also phase shifter. So the kind of graph you have at the end, it depends on the linear optics you do here. There's always a combination of B-splitter, not always 50-50, but and phase shifter, okay? So by controlling actually the linear optics, you can do it. Well, actually, it's not really what people do, because it does not scale so well, meaning that you need to have a lot of squeezer here, okay? So you try to go multi-mode structure of your light in order to do it. And I'm going to give you the specific way we implement in our group, and commenting on the second one that we're also implementing is the one that scale even better. And is the one of using spectrotemporal modes, okay? So what we do actually is that we use the same process, just parametric down conversion process, in a multispectral regime. This is what we do at first. Why is multispectral? It's multispectral because it's your quantum optics, your nonlinear optics that it is. Meaning that for the one that I use to Chi2 process, the phase matching allows for many optical frequencies that can keep being generated in this parametric down conversion process. And we add another degree of control is the fact that we use femtosecond laser as pump, meaning that they have a broad spectral structure. So by playing with these two terms, in a way are the one that come before is the C factor I was showing before. I can manipulate actually the multi-frequency production. So a way of representing this process is to have this multi-mode structure where you have ADAG MAN term, meaning that at each time you have a couple of photons coming out at different frequency, okay? And these terms really depends on what is called the phase matching and the frequency component of the pump, okay? So imagine that this LMN is a real matrix, coupling different frequency. Well, you can diagonalize and you get this Hamiltonian, okay? So you see that here you have actually this SDAG are creation operator for different modes that I call F just not to confuse them with the A. but I just creation operator power of 2, while here you have combination of ADAG of different modes. Well, actually, this is a squeezing Hamiltonian. Okay, if you remember, actually, the difference I was showing before between the squeezing and the parametric down conversion, where you have the two fields that are not degenerate, is that on one case you have ADAG square, on the other case you have ADAG S, ADAG E. Okay, so this Hamiltonian is giving me a bunch of modes that are squeezed. Which one? Well, it depends on the linear optic transformation, or I mean, is the basis change that I do by doing my diagonalization. Okay, I mean, here you have, I'm writing this Hamiltonian in the what we call Frexel, is the frequency degree of freedom. I have different frequency bands, okay? And now I get a basis change that bring me in another set of modes that are not more this frequency, okay? And actually, what happened in our system, if you don't do anything special, meaning that phase matching function are very often sinc function that you can consider to be more or less Gaussian function. I send a pump that is, I mean, can be described as a Gaussian more or less. Well, these modes, the one that I diagonalize this Hamiltonian, are Hermite-Gauss modes in frequency, in optical frequency. So this is our optical wavelength, if you want. Okay. And then actually, I can use an extra step, which is the one I'm going to describe more, which is the way I decide which mode I measure, which set of mode I measure, in order to implement my linear optics transformation. So this is something, so I'm showing my colleague because he started, Nicolas started this, this kind of shaping of cluster state long time ago. Continue to have, and also we add extra stuff. It works because, and giving the full picture, and then actually I recommend again what I've told, because I know that it takes a little bit of time to understand what I'm speaking about. The way we can do actually is that this linear optics is not more linear optics, but actually is done by choosing the measurement basis. And then the way we do it is because we can choose the modes that we measure with our local oscillator, because in femtosecond optics, you can shape, it's called pulse shaping, but that is, you shape the spectrum, okay? You have a femtosecond spectrum, it means that it's something like, it depends on the wavelength of the system that you're using, but could be something like 1240 nanometer wide, meaning that with dispersive element, you can really separate different frequency. You can give different amplitude and phase to the frequency by using a spatial light modulator. So you have different frequencies arriving in different zones of spatial light modulator. You can recombine them, and then I mean, if you start with a Gaussian spectrum, at the end, you get a spectrum that can have any shape, okay? So you can do it with the local oscillator of your homodyne. Homodyne is a mode selective, is a projective measurement, meaning that if your state is composed by many, so think about just frequency, okay? Is the easiest way. Imagine that you have many frequency in your signal, meaning that you have many modes, okay, in your signal, in which you have embedded your quantum system. You're smart enough, you have a very strange quantum system there. On the other side, you arrive with a local oscillator, okay? If your local oscillator has only one of these frequency, well, actually at the 50-50 discrete, what you are doing is optical interference. So you have only one frequency that is interfering with this local oscillator. So this is the one that actually you can measure with your homodyne. So the spectral component of your local oscillator is the one that decides which frequency you are measuring, okay? And I think I have, yeah, this is just to give you a little bit the idea. So I'm telling you that in my system, naturally, if I look at the basis that diagonalized the Hamiltonian before, which is the Hermite-Gauss basis in the optical spectrum, I have squeeze state. What does it mean? It means that if I send this spectral shape as local oscillator, I measure squeezing. Okay? And there is no correlation between this, the quantum state of this, a bunch of squeeze state totally uncorrelated. But actually, I can look at the correlation, but I can send a local oscillator that this is the superposition of these two modes. What I'm doing here, I'm doing a B-splitter transformation. By sending this local oscillator, I'm doing at the same time the measurement and the B-splitter. Why? Because measuring on this basis, it means that I'm projecting on this basis. So it's really like I'm doing the B-splitter between these two modes, and I'm measuring. So I have my two squeeze state on a B-splitter, and I'm measuring that. So on this mode is one of the two that define my EPR state. Of course, I have to look at the one with the minus here. It corresponds to the one that come out from the other side of the B-splitter. If you are lost and you're telling yourself, what the hell she is telling, it's normal. I know that it takes a little bit, but I mean, the only thing that you have to think about, why it's difficult, because it's not a real B-splitter. In the sense, what we are doing, if we speak about different paths, okay, and I have two squeeze modes on two different paths, I put a real B-splitter, and then I look at the real output, optical output, and there I have entangled state, okay? What I'm doing here is that I'm doing a B-splitter for the frequency mode. I'm not putting a B-splitter on my system. I'm telling that what is doing my measurement by selecting specific superposition of mode is like if I was doing a B-splitter transformation. But what is a B-splitter transformation? It's just a orthogonal unitary transformation that you can write mathematically, and then you apply to the modes that are frequency mode now, okay? And it's what is doing the local oscillator here for the measurement of quadrature. It's not always true that we can do B-splitter between frequency modes by doing this. It's true because I'm measuring amplitude of the field. This is important. Because doing B-splitter transformation between two frequency fields, meaning that I want to transfer some energy of one field to another field, meaning that I'm doing, for example, I'm measuring energy and photon counting, it implies that you need to have nonlinear optical processes that make the different frequency speak each other. I mean, this is I'm telling you just because I don't want you to come back to a home telling, oh, nice, I can do, I mean, what I'm normally B-splitter, it means that you're taking part of your fields on one mode and you're transferring to another mode, okay? Well, if you want to do with mode at one frequency to another frequency, it's not always easy. You really need nonlinear optics. Except if you're looking at the amplitude of the field, you can do, if you look at qubits that are just single photon qubits, because actually you have that the amplitude of the field for your single photon qubit corresponds to the wave function, only for one photon, is not anymore true with two photon states. So there's some subspace in which you can do this transformation between different frequency by just doing superposition and smart measurements and sometimes real B-splitter. in general, if you want to transfer some energy from one frequency to another, you need to have nonlinear optical processes in optics. Okay, so this is just one. Okay. Yes. By changing the modes of the local oscillator in which I measure. So meaning that this mode is equivalent to one of the two that is coming out for the EPR state. Of course, if I want to measure the correlation between this mode and this mode, I need to measure also the other, okay? So here, I mean, I can just measure one mode at one time, but I can decide in which basis I'm measuring. Yes?
Relating to what you just said, does it mean that, for example, I understand that the example you're giving is that the mode here are frequencies.
Yeah.
And you just think that to read out from specific frequency, you don't use your local state. From my understanding of lasers all have like a narrow boundary. So I'm guessing is there like crosstalk between that, that fact that the boundary of lasers are very narrow. Does that cause a problem regarding the noise of your final output or the readout?
So not really, because actually the crosstalk comes mainly from nonlinear process very often. So this is here in this process, everything is linear. But if I keep your reasoning, I continue on your reasoning a little bit, or maybe, I mean, just to shift a little bit the focus, is that in principle, if I want, for example, to characterize my multi-mode system, okay, in the case where I have many paths arriving, okay, and I have an interferometer, I have multiple outputs that are physically separate, I can measure all of them at the same time, which is something that I would like to do if I want to do quantum computing processes. I want to be able to access at any moment, any time, a couple of modes, the three modes, the full modes together. Okay. In what I'm describing here, I can measure the modes in any basis, but only one by one. So meaning that I'm measuring, I choose this one, and I'm measuring the output of one of the two modes coming on the B-split, and I have to set the other one in order to measure the output of the other. I can always play with the fact that measuring superposition is giving the superposition. So I can measure cross correlation between a couple of modes, or correlation in a large mode, but I can never measure all the output at the same time. Even if I'm very, I mean, this is very versatile in terms which are the set of modes that I'm looking at. What does it mean that I'm very versatile? It means that doing this shape of the cluster or this shape of the cluster, it just means that I'm just choosing the set of bases that I'm looking at in my local oscillator. So I start with Hermite-Gauss basis. For example, the one that I'm picturing here is exactly the one when I start from this basis with squeeze state, the one that I need to see this correlation that corresponds to this linear cluster. If I start with Hermite-Gauss mode that are all squeezed, and I get these modes that are kind of strange, these four modes are linked together by the entanglement correlation that corresponds to a linear cluster. Meaning that this mode and these modes behave like if I have applied a Seaside operation between the two nodes at the beginning here, for example. How I can measure this correlation? If I just want to measure the correlation between these two, well, again, I send the local oscillator superposition of these two. And actually you can see that, for example, in the homodyne, the variances is given by the variance of the quadratio of the first mode or the second modes plus cross-correlated terms, and there you actually can measure the correlation between the two. So I play a lot, but I cannot measure all the modes at the same time. So this is a limitation of this way of bending the cluster in the same path. The other option is to do mode sorting, meaning that I can physically separate the different modes, and then I can do an homodyne. But again, separating different frequency modes of arbitrary shapes, it requires to have nonlinear optics process. There is one basis in which I can do easily. Can you guess which one it is? How I can separate different optical frequencies without nonlinear optics? Do you have an idea? I know there are engineers in the class. Well, I just use dispersive elements. It's the same thing that I do for dispersing a different element of the local oscillator and manipulate them. So what is called the frequency, what we call the Frexel basis, meaning that we have different frequency bands, is how the multiplexer work. You have a dispersive element that separates the different frequency. And dispersive elements are linear elements. You have a lot of losses there yet, but for sure they are more efficient than using nonlinear process for separating the different mode. Yeah.
Can you use also for above?
For the, sorry?
For above threshold.
Okay, good question. So normally, this specific system that was the first one that was set by Nicolas is optical parametric oscillator is below threshold. And in the below threshold regime is multi-mode. In the above threshold regime, very often what you have in this system is there is one mode that survives more the other. So for example, you have kind of lasing actually on a very specific mode. Then you have a bunch of theory paper that consider the above threshold and how we can keep in a transient regime the multi-mode case. That's true. So me, myself, I don't work anymore with cavities because you can do these processes quite efficiently also in single pass scheme that I'm going to comment. So I still have 40 minutes, no, am I right? Okay. Question. So I know that, of course, when I discuss with a student and come in our group for the very first time, it takes something like 1 or 2 months to understand what is going on this regime. Still, actually, yeah.
Like the connectivity of these two graphs, can it be fully controlled by choosing the amplitude in the superposition?
Yes, actually, in a way. Any superposition of these initial modes can be done, and you have to choose the right one that corresponds to specific cluster. So, of course, actually, let's take a random linear optic transformation. What I get at the output is an entangled multimode state, but it's not always a cluster. So the cluster state has very specific correlation between the nodes that are the ones that are described by this nullifier operator, for example. And the class of multimode entangled state is larger than the one of the cluster. But any correlation that way can be approximated, again, because the exact one, it requires to have infinite squeezing. That is not the case, but can be approximated with this one. So what does it mean? For example, if I choose this one, very often if I don't choose very well the linear optics, I get an extra link, for example, between these two. Maybe is weaker than the one I get on the other, but it's not always so. The multimode entangled state that come out from this scheme is larger than the cluster, so I have to work a little bit in order to choose the right one, but it exists.
So it's possible to have all 4 and then end up killing some.
Yeah. Yes?
Yeah, sorry, a couple random questions. One, someone was previously asking about the crosstalk. Of course, if the spacing between the different frequency cones that are entangled are smaller than the bandwidth of the integration time phenomenon, then it will be crosstalk, right?
Yeah, I mean, also on the other way, we are very limited in this system. So, for example, so for example, in this scheme, my colleague measured at the beginning, I don't know, at the maximum was a 16 squeeze mode. And then actually you can think that you can play with 16 squeeze mode in order to get any things here. But you should be able, for example, this one is a little bit hard to shape by the pulse shaping, okay? And it's even more, actually, you don't only have 16, so probably have 100 of modes that are squeezed. And you are limited by different effects. One is the fact that you have a limited resolution of your pulse shaping technique, which is in general with the kind of system that we can have is quite large. You speak about optical complexity, they can go up to 100, 300, meaning that in principle you can handle 100, 300 modes. But when the shape of these modes is very strange, which means that, for example, in one band, if you're used to SLM, you would like to have one pixel line with a phase shift of pi with respect to the other pixel line. It's dead. You cannot. It's one limiting factor. The other limiting factor, for example, if you look at this basis, is that their mid-gauss bases go larger and larger as you increase you go in the hierarchy, you go far in the hierarchy. I mean, the larger bandwidth, I mean, of course you can shape the local oscillator as you want, but you should start with a very large bandwidth. So if you really want to look at the full basis, you should start from a local oscillator that has a bandwidth that is larger than the original laser that you used to get the system and so on. So yeah, in practical, you have this limitation.
And then just to follow up on that, so I'm struggling with understanding how these pictures on the left-hand side represent positive states. So my question is basically, have SPEC that's happening, you can think that basically that you have a phase matching bandwidth profile, and basically you have pairs that are generated relative to the phase matching bandwidth center. So it seems like to me what you're doing is that you have these collections of pairs that are created, you separate them in frequency, and now you're flipping the phase out of the pairs for that.
Yeah, it is done by the pump. You have the fact is that you have not only the phase matching function, but you also have the function of the pump. If the pump is just one frequency, the correlation you get at the output of the system is just correlation, pairwise correlation among the central frequency of the phase matching. I use the pump to reshape this. And actually, this is already multimode. I mean, the multimode is given by the phase matching mainly, but it's multimode in a very specific situation, actually. I can play with my pump in order to get the correlation. Of course, I cannot do anything. If I use a Gaussian pump, it's multimode, but you look at the diagonalization of is a principal value decomposition at the beginning, what you do in a general case, and you see that actually you get a mid-Gauss mode with this kind of terms. I don't know if there is an easy way of looking at why they're shaped this way.
Yeah, I would have thought that you would have just like complete cancellation. You have things that are just opposite. I'm just driving to the positive phase here, and then off residence the same amount to be negative. I would think you just get nothing.
I mean, for getting exactly these mid-Gauss basis, you need to have a pump that is Gaussian, and you need to be in the case where you can approximate also the phase matching as Gaussian, and really depends also on the mutual bandwidth of the pump and the phase matching. More generally, if you have to consider also the real sink structure, meaning that the bandwidth of the pump is larger than just the central lobe of the phase matching, you have all these wiggle term entering, and you have very strange modes appearing. And we also have to think about how precise you could be in describing your phase matching function in order to diagonalize in a full radius.
Thank you.
You're welcome. Okay, so think about the facts. I mean, keep thinking about how this frequency domain can be used to build cluster. If you don't really believe for the moment, behaves like if you believe me, we can really discuss more, but consider that in these spectrally multi-modes, you can embed different clusters. So this is actually the way they have been measured, the fact that you measure the nullifier. Remember, I was telling you that this nullifier are the one that for the perfect theoretical state, the value should be 0. For the approximated one, as we don't have infinite squeezing, it's just the variance is below the variance of the vacuum, like in squeeze state, okay? So actually what you do, you measure the nullifier of the different nodes, and then you see that they're below. So 0, I mean, is normalizing the way that the shot noise is taken equal to 0 in dB. And actually you can, so these are the different, it's always hard to comment this feature because you have different statistical value. You have the value of the different nullifier, then you have the variance, or you have some other statistical, so you're thinking to the quartile, some of it. But I mean, they just give you an idea on how actually they spread the different value of the different nullifier that you get for the different shape, okay? So the point of this way of doing or producing cluster state that is very easy to change from one to the other, because you can do by working on the local oscillator, but you cannot measure all the modes at the same time, meaning that if you really want to use them for doing quantum information processing, in principle you would like to access any mode at any time you want for doing any general transformation. Another point that, I mean, as we were telling you, are of course limited. The real limitation is how many of them you can measure, and is really given by this optical complexity of reshaping the local oscillator. And practically on the width of the local oscillator, experimental in our case, meaning that in the system that we have measured up to 16 modes, even if you can have 100 that you can use. So it's still a low number if you want to scale actually this cluster state. So, and the way of scaling it is that we want to keep this degree of freedom, but we also want to use the time being degree of freedom. That is the way the very large cluster that I was showing in the state of the art beginning have been generated. So what I have done in the last year actually is to work, meaning that we really want to build something that goes beyond actually this 16 mode structure, is to use single pass squeezing process. So we don't use any more cavity. Why we don't use cavity? Because now that the cavity introduces a bandwidth, and the one that you can build, the bandwidth is not compatible with the pulse structure that we have, meaning that you have the bandwidth of the cavity that is some megahertz, could be up to 10 megahertz, but actually you have pulses that arrive with repetition rate for femtosecond modulo laser, could be 100, could be also gigahertz if you want, but it could be 100 of megahertz. And you would like to preserve this time-being structure that arrive with pulses. So this is why I went to single pass processes and no more in cavity. By using periodically poled material and waveguide. So actually I get rid of the cavity, but I need to, I mean, why use the cavity? Use the cavity because actually this process happened many times before they failed. So you are increasing the nonlinearity. So the Chi2 terms is normally very low. So you want to increase the nonlinearity. And you can do with cavity or you use waveguide because I mean you focus the mode of the field is more. So by using periodically poled KTP waveguides, actually what you want is that at each time you have one pulse arriving, this pulse is squeezed, and you can see the squeezing here and the squeezing here. Yeah.
It's not poled.
It's not poled. It's waveguide.
Wave, so it in principle does have multi-passing, right?
It has, sorry? Yeah, you cannot. I mean, you cannot really use it with a cavity. This was the question, or no?
No. So it sounded like you were, your phase matching bandwidth profile is still being selected by, it's effectively the same thing as cavity, right?
Yeah.
Okay. I think you're suggesting that you could do this with both, right? But I don't think it works.
So actually, if you look at the multimode feature of the system, is exactly the same as in cavity in the sense that it's driven by the phase matching and the pump structure. Of course, sometimes, if you go back to the cavity, you should be smart enough to have a cavity that does not cut somewhere this phase matching. And especially when you have pulses, you have to really control the dispersion of the different frequency arriving. So you have, in a way, you have to be smarter in the cavity to be really multimode and keep the full structure of your phase matching and of the pump that you don't disperse.
Okay, so for this system, do you have multiple FSR peaks inside of the phase matching? One peak?
No, actually, in the cavity you have one. So you have, actually what we use is if you look at the time domain, synchronously pumped cavities, SPOPO, meaning that you just have one pulse going on one time in the cavity, so you really get, or if you look at it as a frequency comp, so your cavity really match the frequency comp structure of the femtosecond laser. So in a way, being multimode is harder. In the cavity, you really have to control the full dispersion. If you just send the laser, even without the nonlinear optics, can be dispersed in different, the femtosecond laser can be dispersed in different way, the frequency into the cavity if you don't control the dispersion of the mirror and so on. And then you add also the... we preserve the multimode structure that is mainly given by the phase matching function in this system, and the pump is just this Lij matrix that was in my Hamiltonian A DAG AJ before. Meaning that at each pulse, I still have my several optical modes in optical frequency that are squeezed. If at this point, and I'm telling you that this is a way of multiplexing my system, because I can use both the time being degree of freedom and the frequency, optical frequency. If you start to get confused there because in your mind you think that frequency and time are just one, the Fourier transform of the other, so you don't understand why I'm speaking about getting two different degree of freedom, in a way you're right, in the sense that the fact that here I'm using the time domain and here the frequency domain is just the way I manipulate these two scale in my experiment. But if you want actually take these different frequency modes, optical frequency around the central frequency, always the central frequency that I use in my laser actually, in the frequency domain, and you make the Fourier transform, okay, and you get time mode. And actually what is nice with the Hermite-Gauss is that the Fourier transform of Hermite-Gauss, you get exactly Hermite-Gauss. It's like a Gaussian, stays for all the elements. So actually I have very fast shaping in femtoseconds in this case, and then these are repeated at a scale that is nanosecond. Okay, and this is the way actually I get my multiplexing. If you want, is a coarse tuning and a fine tuning. You can do the same with the frequency. You keep frequency here, you imagine that this is coming, you're repeating with the repetition rate frequency of the laser. I'm telling it because I often get this question, but it's not really different, the degree of freedom. Well, or you can tell yourself that this is the degree of freedom of different wavelengths and the way you combine them, and then also you have the time beam. Yeah.
So at this stage, are you generating like for each state?
Not yet. These are the building block. Well, actually, then it depends what you mean in three-dimensional. In the sense that you can also devise in the frequency domain a linear optics transformation that gives you a three-dimensional graph. Okay, the three-dimensional that I use in this way is just really I want to use two different degree of freedom from the planar structure and this structure, and really one keeping that is the time. Okay, for the graph it depends what you do, but I mean this is the way. For the moment, I'm just having the building block. Of course, if I want to have three-dimensional structure, I have to generate entanglement correlation at different time, which is not yet the case here. I get by free the entanglement correlation in the frequency domain by shaping my local oscillator and using it. Still the time I need to do something more in order to get the entanglement. For the moment, it's just the multiplexing here. Okay, this was just to show, so, well, if you want to look at this multiplexing, you just need to have a detector that is fast enough in the homodyne case in order to see pulse by pulse, and you still shape the local oscillator in order to get the different frequency structure. And here are the results that we got with a system that in a way very similar to the one the cavity, meaning that we work at near infrared. But the way you can interface the nonlinear optics and this wavelength shaping is such that you need to have very short crystal, and so you don't generate too much squeezing. So we moved to telecom wavelengths because actually the frequency structure that you can get there, that you can shape, is more compatible with the one that you generate when you generate a bunch of, so meaning that this bunch of spectral modes are not too large compared to the original laser that you want to use as a local oscillator, even if I use a long crystal, okay, a longer waveguide. And such way I start to have squeezing value that are not bad, that are around 2.5, and very recent in the same setup, now we are measuring something like 3 dB of squeezing, which is also the one that you get normally for free in the cavity. I mean, I'm not telling that I can do fault-tolerant quantum computing with this amount of squeezing, which is not what I really want to do, and this is going to be clear more tomorrow, where I start to speak about protocols, okay? But it's not bad, especially because you're in a multi-mode structure. So what is the extra term that is missing is exactly what has been done in the group of Akira Furuzawa and Ulrich Anderson a bunch of years ago, which is in order to get entanglement at different time beam, I need to have delay line and B-splitter. So this one is the scheme of the first experiment that Akira did, where you have two different OPO producing squeeze light with a specific bandwidth. Actually, you can define a bandwidth of, I think at that time was 6 megahertz. And now he has a structure that is more compatible on fast repetition rate. And then actually what you do, you have squeeze. I mean, you try to have squeeze state along two different directions here, meaning that you have a lot of lock on phases that you have to do. You mix the two on a B-splitter and you get, so actually here you see I start to build a two-node cluster this way. You get one of the two that is delayed exactly by the inverse of this is megahertz and bandwidth, actually. That is a lot of nanoseconds now, I cannot tell you by heart. And then you mix again a B-splitter. And this way you get for free, this dual is named dual ray structure. So meaning that, so the difference on this node and this node is that you are a different time, okay? And what you get is that this node on this path at this time is linked to the node on the other path at the same time, but this one is also linked to this node at this time, and then you get all this kind of correlation. Meaning that really you can apply it's like you have applied Seaside operation in this way. And then the structure is going on, okay? The one that I was showing you in the state of the art, where you have this kind of Edica structure or more strange structure, is done by getting either a third a beam here, and in any case getting more linear optics and delay line elaborated things. You can get several, actually, depends. But actually it can go on in time as long as you want. It really depends, actually, the fact that you can have a node that is correlated to another node, to another node, to another node, and you have millions of nodes in time that are correlated so far. It depends a lot on the coherence, on the optical coherence of your system. Then, of course, compared to the class that you can build either with spatial mode or frequency mode that are all there in your system at the same time. So in principle, you can measure that at the same time. When you start to have this time-being structure that goes for thousands of modes, well, you have that one mode is correlated to the one that is not yet generated by your system in the parametric process. So your class is not always there, all the nodes are not there at the same time, but you can you can devise a way of doing quantum computing where you have, this base structure that you measure, then actually do measurement on the other one, and you have feed forward and other, let's say, practical way of building your calculation. In any case, you never do your calculation of the same, or all the steps of your calculation at the same time. Actually, have just to be fast enough in order to catch up with the cluster structure that is coming. So what is still not it's in the lab, but is not out yet, is that we are trying to mixture. So this structure, and then can be done helicoidal, has been already done up to 1,000, 10,000 nodes. We want to add an extra layer of having entanglement correlation between different frequency at each node, which implies the fact that still we need at least two different waveguides where you can play this game of mixing and adding delay line. And then actually you need to have a fast modine detection with this local oscillator can be shaped, in order to generate kind of arbitrary structure where you have different optical frequency nodes that are entangled each other, that are then entangled with the node that come at different times. So this is really the picture in which we are. And this is, is exactly what I'm telling, is the fact that this two-dimensional structure, we want to use the time being on this direction, and the different frequency modes on this direction. Okay. Do you have questions? I know that you have, but you are not able to formulate a lot of them, probably, no? Yes.
Next step is to better
So if you really want to go there, meaning the universal quantum computing, it's hard. Also, if you also want to add the layer of the fault tolerance, but it's hard in any system for the moment. So it's feasible, I guess. Yes. I don't really picture how, the most advanced in this scenario is Xanadu, okay? Because they did this GKP state. still the rate of this GKP state is not so fast. Still, you need many of them. Still, is not really okay. So this is also the fault tolerant part. Okay. On the other side, what I'm doing and want to do are not fault tolerant quantum computing, universal quantum computing step. I think there is space of other, so either quantum communication scenario or quantum computing not universal. That could be a subset, for example, of kind of machine learning protocol that can be done, and in which we can already get some kind of advantage compared to the classical case. The full stack quantum computing, let's see, I guess that we need to have something more. I'm not sure that stay fully optical we can get very fast. Probably we can try to match this system with others. I mean, I was showing at the beginning the fact that the GKP state can be produced very easily in microwave. Sometimes they have hard problem of getting the multimode, and even if you get there, actually, you know that in any case, especially if you're in this workshop, optics is necessary because you want to get some communication. The communication also in distributed computing and so on should be probably done by the optical part. But maybe we also need to have some system talking with the optical scenario too. Yeah.
So this generation energy can be set up high order.
Yeah, actually, the way Xanadu does it, they use the boson sampling experiment. I'm going to speak a little bit also on the post-selecting on non-Gaussian state tomorrow. But what they do actually is that they, by post-selecting, meaning by getting a certain number of photons that are counted on different modes, they post-select on the remaining mode this GKP state. And I think you need, so I guess they have, I don't know how many negative region, you need to count a photon for any negative region. So meaning, so if they get 9, means that they count 9 photons at the same time on a bunch of modes in order to get the other. So you see, I mean, it scales like this. And still is something that you cannot really use for doing for tolerant for the moment. But I mean, it's a great, so to tell you, I'm kind of excited on what they have done. Of course, I have two kind of mind. I mean, I'm very excited how, I mean, by pushing technology is evolving, and you have a lot of stuff that is going on right now with very nice results. Of course, I also have kind of scientific, academic grounded quantum physics point of view where, I mean, well, we have to be careful on what we are selling is not yet the quantum computers. But I think, well, at least the universal one, I think they are still sub-universal, in any case, very specific task that we start to be able to do in the quantum scenario, at least potentially, they can be useful for specific tasks or subtasks. Universal quantum computing is not there yet. Okay, if you don't have other questions, I want to go a little bit back to my interlude that I was kept. Which is this one, and again goes with the idea of challenging you on this idea: what is continuous variable, what is discrete variable, and to stress again the fact that is more about what you are measuring than what you are producing as a quantum state. Is because that could be that some of you, when I started to speak about parametric down-conversion processes, you have been told several times that these are the kind of process that has been used for a long time to generate single photon states, okay? Which are kind of a fully DV scenario, okay? And that's true. because what I do is that I count photon. And I mean, nowadays is no more the most efficient way of producing single photon. Depends what you're doing, but let's say at least in terms of brightness and how many you can measure, you can count on a specific time scale. But I mean, it's kind of historical, it's still used, and well, the idea is that in the non-degenerate condition, I also was referring to the quantum vision of this parametric process by telling, oh, you have 1 pound photon that transforms 2 photon. Well, yes, when the nonlinear regime, I mean, the chi2 is very small, and you post-select by counting 1 photon on the other part, you get 1 photon on the other one. It's not enough to say that G is small. So I'm calling G in this picture actually the nonlinear. Because if G is small and you don't post-select anything on the other, and you measure, mainly with homodyne setup, without post-selecting, you get a thermostat. Okay? You need to post-select on a specific number of photons. And I mean, and if you post-select and you describe in continuous variable, you really get the Wigner function of the single photon on the other side. So these are experimental data that take a long time ago in my PhD life. Yeah, you post-select, you get a single photon here, okay? But you have to post-select. Naturally, if you don't post-select in this system, you get the EPR, the continuous variable EPR state, the 2-mole state, okay? That if you just measure one, the signal by pre-discarding the idler, you get a thermostat. If you are able to measure all the quadrature correlation and to reconstruct the Wigner function, this quadridimensional Wigner function, well, you get the 2-mole state, which is exactly what it is coming out from the system. And you can also look at the statistic of photon coming. I mean, sometimes you have only 2 photons. And when you click on one side, you get 1 photon on the other. If you have a gain that is large enough, you also get all the other terms on this series. So in the Fock basis, this is the state they are producing. If lambda, I mean, I know I'm using lambda, Xi, G sometimes, it's always the same thing. It's the nonlinear term actually they're able to produce with your nonlinear optics. If lambda is small, I mean, the probability of producing 2 photons on the other side and 2 photons on the signal side is kind of low, but it's still there. Okay? And probably here also you can see that the states can be seen as being entanglement, not only in the continuous variable, not only looking at quadrature. You really have correlation, exact correlation on number of photons that you get on the one side or on the other. And then if you go degenerate, you get the squeezing. That is always the same process. Parametric down conversion process is not the process that produces a couple of photons. Is the process that's produced a 2-mole squeeze state if you are in a non-degenerate condition. It produces squeeze state if you are in a degenerate condition. And if you are in a case of the very low gain and you post-select on one of the channel, you get a single photon on the other. You can also be in a kind of intermediate regime where you post-select on 2 photons, 3 photons. I did 2 photons, I have colleagues that arrive to 3 photons, and then it's a way of producing not very much efficient way, a 2-photon Fock state and a 3-photon Fock state. But the way you interact with your system and the way you measure is really the one that defines, at first, if you are producing or not producing a state that is better or not better described in the discrete variable and the continuous variable regime, that for the description of the quantum state are totally equivalent. And then you can decide if you measure, you count photon or you measure quadrature, the way you want to encode your information and process your information. And you need to do the full stack in order to make the difference between continuous variable, discrete variables. I mean, the idea that you have continuous variable state and continuous discrete variable states is kind of wrong. So this is my point. Quantum state is a quantum state. You can describe both in discrete and continuous. Then when you go to information, you can try to encode in specific states the kind of correlation that you want in order to do quantum information and so on. Okay, I think I'm going to finish here. Thank you for attending. Do you have further questions? Well, we have other to lecture tomorrow, and I'm staying here the full week. So you have time to think about what I told. If it's still not very clear, come to me and ask questions. Thank you very much. Thank you very much for the question. I really appreciate it.